Load it. Yeah.
In the first part where we need to find the differential equation of the motion using MATLAB. So that's essentially like the Euler-Lagrange, right?
So Euler-Lagrange would create an MATLAB function ODE1.m. That ODE1.m is the differential equation of motion in the first order form. Now the question is, how would you decode that equation in pieces? Just take a look at it. And I would spend some more time on that. So I don't want you to find the second order differential equation. Whatever differential equation that is given in Euler-Lagrange output, ODE1.m, that first order equation, you can say that that's the differential equation. You can take that first order equation and convert that into a second order equation, or you can use the first order equation for control. But I haven't talked about the control. Any other questions? Okay. So in today's class, I'm going to talk about the controls. So robot control. So how many of you have studied one or the other type of control before? Anything related to controls? EID. Okay. So why do we need to control? Basically, whenever we have a system or a robot that may not behave the way we want. So what we want to do is, we want to change the dynamics of that system or the robot so that it meets the required specifications. So what do I mean by control? Control means making robot stop or making robot move the way we want. Now this sentence implies two things. It could be sort of a set point control. What it means is you want your robot to get to point 10 and stop there. Or you want your robot to be like a trajectory control, which means you want your robot to move at a constant speed. So when you look at the control, there are two things that we need to consider. So there is something called as the open loop control, or system runs on open loop. In open loop, you have a system, you provide the input, and then you get an output. So this could be a robot or it could be a system. And you have an input and you have an output. So there is no feedback. So this is an open loop system. And then you can have a closed loop system. So in closed loop, you have the system. Then what you do is you have an output and you tap some part of that output and then actually feed it to a summing junction, which is over here. So this is the feedback. So this is closed loop. Now, let me give you an example of an open loop and let me give you an example of a closed loop. Imagine if I start teaching without looking at you or without gauging whether you have understood the concept or whether you are following what I'm saying, then it would be like teaching in an open loop. So I don't care whether the material that I'm trying to convey gets conveyed properly, whether the students learn and understand, or what I do is I ask for a feedback like, hey, have you noticed this or have you understood this? Then I change my teaching strategy based on the student engagement, student feedback, that would be teaching in the closed loop. Open loop systems are easy, and sometimes open loop systems, they work. A classic example is the 3D printers that you use in Innovation Hub, or the 3D printers that you have at your house. The 3D printers are run using a stepper motor. Stepper motors do not have a feedback. You give a pulse, and depending upon the pulse, that motor moves. And then you assume that depending upon the signal that you have given to the motor controller, the stepper motor would perform the motion, linear or rotary, whatever motion that you want. In the case of closed loop, you would have some kind of a feedback or an encoder or some kind of a resolver that would create the feedback from the motor that will be used to correct or rectify the input. That way you can either actually track the output that you desired, or you can actually do a set point control. So there are two types of controls in terms of robotics. One is something called as the set point control. And the second one is tracking control. So what do I mean by set point control? Imagine that you have a car, okay? And what you want is you want this car to stop at point A. So this is the set point. So the car is moving, and you apply the brakes in such a way that this car stops at point A. That is a set point control. Now, in the case of tracking control, let's say you have the car and that is going down the slope, but even though it's going down the slope, or whether it is going on the level road, or whether it is going up, you want car to be at maybe 20 miles an hour. So 20 miles per hour. So as it is going down, gravity would assist. So you would be applying brakes to maintain the 20 mile speed. On the level ground, you will maintain the 20 mile speed. And as the car is going uphill, at that time you would have to give a little bit more gas so that the car picks up the speed, but it maintains 20 miles an hour. So this is the tracking or trajectory control. The other thing in set point control would be either going to a fixed point. Say for an example, just like your thermostat, you set your thermostat to 80 degrees. So what's going to happen is the air conditioning would get turned on, go to 80 degrees and turn off till the temperature drops. So that would be a set point control. So it could be going to 0 or it could be going to a fixed point. In the case of tracking, what you want is you want that thermostat or you want that air condition to cycle the temperature through a particular cycle. So you want that temperature to go up and then go down, then go up and then go down. So your thermostat should adjust in such a way that that thermal profile can be achieved. That is called as tracking control. So you could have a set point control or you could have a tracking control. And now what I want to tell you is in this class, we are going to focus more on the linear control. So we are going to talk about linear control. And at the end of the day, linear control, whether you study the control in PID as PID controls or you look at state space, the fundamental idea is the same. And we talked about this, but I just want to emphasize on this concept. Whenever you have a linear system, the linear system is given by maybe x dot is equal to ax. Remember we talked about this, x dot is equal to ax, where a is a scalar quantity. Scalar means just a number like 5, 6, 7, or x dot is equal to ax, where A could be a matrix, which means it would be something like this. Now, I want to emphasize once again what dictates the stability of the system. So, x dot is equal to ax. How do I, when can I say this system is stable, asymptotically stable, or unstable? So, once again, I'm going to talk about the first. When A is equal to 0, your response is going to be something like this. This is time. This is x. Are you with me? When A is less than 0, then your A is less than 0. And if your A is greater than 0, this is how the response is. So when A is equal to 0, this guy, system is simply stable. A is less than 0, system is asymptotically stable. And A is greater than 0, the system is unstable. Are you with me so far? Now here comes the crux part. Whether you study PID or whether you study pole placement, all these controller techniques are focused on changing the sign and magnitude of A. I would repeat this once again. And this is very, very important. Whether you study PID type of control, which is proportional, integral, or derivative, or whether you consider state space control, which will see that pole placement, both these techniques at the end of the day are going to take this A and convert that into either a stable system or an asymptotically stable system. Everyone understood this? Now, same thing happens in the case of the matrix system. The only difference here is you are going to use your PID or pole placement to change the eigenvalues of the A matrix. Everyone understood this? Now, what I want to do is I want to give you a very physical example, a simple example. So, and I'm going to teach this slightly differently than it is discussed in the textbook. So please pay attention. Now imagine that I have a system which is given by x dot is equal to 5x. This system is given as x dot is equal to 5x. And I want to control it with a controller. So what I'm going to do is I'm going to add maybe a controller term. So this is the controller. And this controller, I'm going to say this controller is of the form PID. P stands for proportional. I stands for integral. And D stands for derivative. So I have a controller that I'm using to control this system, which is given as x dot is equal to 5x. And this could be maybe a simple system like a temperature probe. And this temperature probe needs to be controlled. So you have P, you have I, you have D. P means P is the term which is proportional to the state. Integral term is the term which is proportional to the integral of the state, and D is the term which is proportional to the derivative of the state. So what I want to do is I want to first look at just the proportional control. So case 1, proportional control. In proportional control, my state is x. So my controller, I'm going to say x dot is equal to 5x, and then I'm going to add the controller term, which is minus 5x. Are you with me so far? This is going to be my controller term. And as you can see, this controller term cancels out the state dynamics, which means my x dot is equal to 0. In other words, my system is going to become simply stable. What I'm going to do is, I could add x dot is equal to 5x and add a controller term minus 6x. That gives me x dot is equal to 5 minus 6, which is minus x. And please understand, now my system has become asymptotically stable. Are you with me so far? So the controller term is going to modify the dynamics in such a way, either the value of that scalar coefficient would change or the value of that matrix eigenvalues would change. Now, why do we need an integral and derivative term? So if my controller comprises of a term which is proportional to state, then it's a proportional control. If it includes the term that comprises of the derivative, so for an example, plus or minus, say 0.1 x dot, that is derivative, and sometimes you can have maybe some type of an integral term, 0.01 integral x dt, and then this is called as the integral term. So the way the PID works is, you have this plant or you have this system, and then what you have here is you have a PID control, and then you have a summing junction, and then what you do is you take the input, you take the output and feed it to the summing junction. So this is your input, this is plus, this is minus, this is plant or robot or the system, and this is your output. So this PID term, what it will do is, it will actually find out the difference between the output and the input. That forms the error. That error gets fed into this PID controller, and then the PID controller gains either magnify or reduce the value of that error, and then basically manipulate the plant. In other words, what I'm trying to say is, this whole controller would try to change the system dynamics. There are various ways of studying this. You can study the PID control in the time domain. You can study the PID control in frequency domain. You can design the controllers in time domain, and you can design the controllers in frequency domain. Yeah.
The goal of the PID is basically force the robot to set value.
So every controller, there are only two objectives. Either it could be a set point control, which means you want your robot to go to a particular location, or it could be a trajectory or tracking control, which means you want your robot to follow a certain profile. And again, what that means is, here is what can happen, that you want your robot to go to a set point, but basically robot could go and kind of oscillate about the set point, or robot could go and it may not be at the exact set point, it could overshoot or undershoot. Or what could happen is robot may take a lot of time to go to the set point. So you need to design the controller in such a way that it meets with the requirements that the designers have specified. The another example is if you want a trajectory control. So for an example, if you want your robot to follow this sinusoidal curve. So basically, but then the robot, what it could do is it could continue to oscillate about the base sinusoid curve, and you want to minimize those oscillations using a suitable controller. So there are two types of control. One is the set point control, and other control is the tracking control. Now, the best thing to show controller is showing with some simulations what happens. Now, most of you must have taken the basic course in differential equations. Is that true? Most of you must have been exposed to something called as Laplace transform, right? Okay, so can someone tell me what is Laplace transform? And I promise, I'm not going to ask you to calculate or derive Laplace transform or solve, but I want some common sense answer. Yes. Space to time, time to space, time frequency, frequency time, frequency time. Okay.
Time to frequency.
Okay, let me ask you even more fundamental question. Why do we need Laplace transform?
Because convolution is difficult to calculate in Python.
Huh.
Sometimes we might be doing a few fundamentally different variables to get a way to connect them to one another.
Okay, all great answers. I'm sure somebody who has background in mathematics taught you Laplace transform. Okay, I will go a step lower. How many of you know logarithms? High school, right? Okay. Why logarithms were invented? Logarithms were invented to make our life easy. Here was the basic problem. Consider that you have this big number, okay? You are going to multiply this big number by a big number. The resulting number would be a bigger number. You agree with me? Performing that calculation by hand is not possible. As a matter of fact, in 1950s and 60s, performing this calculation by computers or calculators was not trivial. So what happened? Logarithms were invented. What did logarithms do? You apply the log to this big number, it became a small number. You applied the log to this number, it became the small number. And since the multiplication in your regular domain became addition in the log domain, you could add these two numbers, find the resultant, which was very quick, and then find the inverse log that was the solution of this big number multiplied by this another big number. Everyone understood this? That was the fundamental purpose of logarithms. What does Laplace transform do? Say you have a differential equation. If you want to solve the differential equation, what do you have to do? You have to perform integration. Do you agree with me? If you use Laplace transform, then that differential equation gets converted into an algebraic plus or minus equation, which is very easy to solve. And then what you do is you find the inverse Laplace and boom, that is the solution of your differential equation. Everyone understood this? That is the fundamental reason Laplace transforms are used. So I'm going to give you the example. So if you have a big number, you multiply this with a very big number, If you take the log of this guy, then it becomes a very small number. Then you add this to log of this other guy, and then you have this small number. And then you take an inverse log, and then you get this big number, which is the resultant of that two multiplication. Same thing with Laplace transform. If you have a differential equation, say x dot is equal to maybe x double dot is equal to x dot plus x plus sine t or something like that, this differential equation gets converted to algebraic equation using Laplace transform. So Laplace transform, the biggest advantage is you get rid of this integration. You don't have to integrate. You have the differential equation. You take the Laplace transform, that differential equation becomes into plus minus type of equation. You solve that equation, and then whatever answer you have, you take the inverse Laplace transform, and boom, that is the solution of the differential equation. Everyone understood this? That is the purpose of Laplace transform. Now, this would be a good time to give you the definition of something called as the transfer function. Transfer function is the Laplace transform of output divided by the Laplace transform of input. So what I want to show you here is, let's look at the time domain variables. And then look at Laplace domain or frequency domain variables. And please understand, I'm not going to ask you to do any Laplace transform by hand. If we have to do a Laplace transform, we are going to use MATLAB. But I want you to have one-to-one correspondence, so that if I give you a system, you should be able to represent that in as a transfer function in MATLAB. So in time domain, your independent variable is t. T is your independent variable. And in Laplace domain, your independent variable is s. In time domain, your state or dependent variable is x, small x, that is function of t. In Laplace domain, it is capital X, which is function of s. Everyone understood this? The only thing that I want you to remember, and which is super important, is if I have a derivative. So for an example, if I have d by dt in Laplace, that is going to be s. If I have integral d over integral dt, that is going to be 1 over s. What that means is, if I have x dot, which is equal to dx by dt, please note this is d by dt x. This will become s, x of s. Are you with me so far? If this equation is x double dot, then this is going to be d by dt, d by dt x, and this is going to become s square x of s. Are you with me so far? So with this knowledge, what I want to do is, I want to give you a simple system, and let's try to design the controller for the system and see what happens. So everyone, I want you to look at the board. So consider a simple spring mass system. I have this spring mass system, and this spring mass system has stiffness K is equal to 1 and mass M is equal to 1 kilogram and 1 Newton per millimeter square, 1 Newton per meter. So I have the stiffness, which is 1 Newton per meter, and I have a mass, which is 1 kilogram. And on this mass, what I have is I have an input U of t. And this input could be a constant. This could be a sinusoid, or it could be a ramp, or it could be a step. So this input can be anything. So first, what I want to do is I want to apply Newton's law to derive the equation of motion. And we have done this. So remember, force is equal to mass times acceleration. And we derived something like mx double dot plus kx is equal to u of t. Are you with me so far? So this equation is in the time domain. Now what I need to do is I need to convert, this is very important, I would like to convert this equation in frequency domain. So n is a constant. So now our Laplace domain or frequency domain. So first, let me understand what is my input. U of t is my input. And x of t is my output. So I'm going to apply the time domain to Laplace domain conversion rules that are written over here. Time domain to Laplace domain conversion rules that are written over here. So I want you to see what happens. X double dot would become m. X double dot is this. It will become s square x of s, right? Plus k is a constant, just like m, k is a constant. So it will become k x of s, and u will become capital U of s. Do you agree with me? So what I have is I have the equation in the time domain, and I have the equation in the frequency domain or Laplace domain. Why is this in Laplace domain? Because my independent variable is x and my dependent variable is x of s. Now, what I'm going to do is, I would, please understand, this equation, which was, and this is extremely important point to note. Do you remember in my time domain equation, I had those dots. What do those dots mean? The dots mean derivative. One dot, one derivative, two dots, two derivative. As soon as I took the Laplace transform, those dots disappear. Are you with me so far? And the only unknown, please understand, it's extremely important. The only unknown in this equation is x of s. So if my u of s is known, x of s can be represented as a plus or minus combination of u of s with k and m. Are you with me so far? So what it means is my differential equation is now converted into an algebraic plus or minus equation. Solving that, again, if you take the inverse Laplace transform, you would get the solution. But that is not the purpose here. What I want to do is, I want to find out the transfer function of this guy. What is the transfer function? Transfer function is the Laplace transform of output divided by the Laplace transform of input. This is going to be my transfer function. So what is my output? My output is x of s. My input is u of s. So what I would do is, I would take ms square plus k multiplied by x of s is equal to u of s. So x of s divided by u of s is going to 1 divided by ms square plus k. Are you with me so far? This is my transfer function. Any questions here? Very simple, right? Now, what I'm going to do is, I'm going to go to MATLAB and I will try to solve this transfer function using MATLAB. So this would be a good time to actually run or open MATLAB. And so I would encourage you to start MATLAB. So go to Simulink. Open a blank model. And let's build this system inside MATLAB. So I don't know if you see my screen, but I'm going to write this over here. My transfer function m is equal to 1, k is equal to 1. So my transfer function is 1 divided by s square plus 1. And this transfer function would have some input, which is u of t or u of s. And this transfer function will have an output, which is x of s or x of t. So this would be u of t, and this would be x of t. I don't know if you can see this board, but this is what it is. So I want to build this system, and this system is actually an open loop system because there is no feedback. Everyone understood this? This is an open loop system. There is no feedback. So go to library browser. Go to library browser. And then continuous. And then what I want you to do is, I want you to grab this transfer function, put it over here. Grab this transfer function, put it over here. And then can you see that the way this transfer function is showing 1 divided by s plus 1. But I want this transfer function to be 1 divided by s square plus 1. So this transfer function is nothing but 1 divided by s square plus 0s plus 1. So which means the numerator of this transfer function is 1 and the denominator of the transfer function is 1, 0, 1, 1, 0, 1. So I want you to go to the numerator coefficient that would stay as is, but the denominator coefficient would change to 1, 0, 1. Click on it, and now can you see that this has become the transfer function? Are you with me so far? Yeah.
Mine says news over dense.
Now what I'm going to do is, this is going to be my input and this is going to be my output. So I'm going to apply some inputs and see what happens to the output. So a very quick question. If you have a spring mass damper system, if you pull the mass, let it go, what would happen? If you pull the mass, let it go, what would happen? It will continue to oscillate. If there is no damping, it means there is no energy dissipation, it will continue to oscillate for an infinite period of time. This pulling and releasing is nothing but supplying a step input. So a step input. So if I apply a step input to this transfer function, what I should see is I should see this system to oscillate continuously. Are you with me so far? So what I'm going to do is I'm going to go to the source, then go here. Can you see this step input? Grab this step input, put it over here, add it over here, then go to library browser, sync, go to scope, add it over here, put it over here, and then what you do is basically run. And you would notice if you double click on scope, you can see these oscillations. If you want, what you can do is you can actually make 2 scopes and feed this signal. So basically feed this signal over here, feed this signal, and then actually connect this over here and then run. So now what will happen is you will see your input, which is shown by the blue line, and you will see the output. Does it make sense? This system is a simple spring mass system. You provide a step input to the spring mass system, and the spring mass system would continue to oscillate for an infinite period of time. Are you with me so far? Now, what I want to do? I want to control this system. What do I mean by controlling the system? Controlling is somehow I want to change the dynamics of the system. So what I'm going to do is, we are going to talk about this a lot, but let's copy this transfer function. Copy transfer function. And this is my open loop. What I'm going to do is, I'm going to go to my library browser. I'm going to go to the continuous. I'm going to use this PID control. Grab this PID control, put it over here. Then go to copy this, paste it over here. Then copy this input, paste it over here. Then go to library browser, commonly used blocks, and then you will see this summing junction. Grab this summing junction from here, PID, and then take the feedback from here, and this will be connected to input. So, and this summing junction, I want you to note that right now, this is adding the feedback to the input. Adding feedback to the input is positive feedback, which is dangerous. So we need to convert this feedback into a negative feedback, which is plus and minus. So make it plus and minus, click OK. Go to this PID. And what I want to do is, I want you to look at, these are the three constants. And if you look at the transfer function for PID is given as P multiplied by the integral of the state multiplied by I multiplied by the derivative of state multiplied by D. So P is the constant of proportionality that multiplies the state. I is the constant of proportionality that multiplies the integration of the state, and D is the constant of proportionality that multiplies the derivative of state. This PID function is written in slightly complicated form, but what I want you to do is, and we'll spend a lot of time on this, but at this point, I want you to do this experiment. I want you to change this constant of proportionality to 10. Are you with me so far? Change this constant of proportionality to 10. Click OK. Now what you have is, on the top, you have an uncontrolled system, and at the bottom, you have a control system with a PID control. Are you with me so far? Run these two systems and see what you observe. Run both of these systems. And now click this. This is the uncontrolled system. And click this. This is kind of the controlled system. But as you can see, this is not very well controlled. So what we do is we go to PID and then add a derivative term. And now see the controlled and uncontrolled. Are you with me so far? So by changing the values of P, I, and D, you can actually change the system behavior. On the left-hand side, what you have is you have uncontrolled system, and on the right-hand side, you have a system that is controlled. But the problem here is, you would see that my input is from 0 to 1, but my output is not close to 1. It is sort of having some fixed offset. So what you can do is, you can change the values of maybe derivative. So you can make it like maybe 50 and run, and then try to minimize the overshoot. So you can see that overshoot decreases. But then as time goes on, it kind of increases. So you can go back and now add an integral term, say 0.1. So what does PID do is PID and then run. And what would PID try to do is, it will try to control the uncontrolled behavior of the system. So this is the basic application of PID, wherein you have a system that initially not controlled, but using some type of a PID gain, that system can get controlled. Now there is a lot of math that goes inside, but crux is at the end of the day, it is going to change the eigenvalues or the poles of this system. So before I get into the math, I want you to understand what does PID control do? PID control changes the dynamics of the system. The only way to change the dynamics of the system is changing the location of poles or the eigenvalues. And PID control changes the pole or the eigenvalues of the system. And I would encourage you to change or play with these gains. So not with the system, but change with the PID gains. And then you will notice that as you play with the gains, for some values of PID control, that system is going to give you a very good performance. And I believe that when you did the robotic bike or the bike balancing projects, you had to tune the PID gains to make sure that the bike is getting balanced. Now, before I start talking about the mathematics, what I want you to understand is there are many techniques for control, but PID technique is typically preferred because it is simple, it works very well for the linear systems, and even for nonlinear systems, if the operating point is close, which means the operation range of operation is not very far, if it's very close to the operating point, then the PID control could give you a reasonably well performance. Now I have to go back to the blackboard, but before I do that, any questions on what I have shown over here? Any questions on the demonstration here? Yeah.
For the transfer function blocks, is it necessary for the transfer function to actually show? Because once I start editing it, it is going to apply numerator, denominator.
Yeah, just this numerator and denominator. So for an example, if you say something like, if you add some more terms here, then it will be different.
Okay.
So it won't show the numbers. That's fine. It would just show. Okay. So, yeah, try expanding. In older MATLAB, it used to show num versus den, but in newer MATLABs, if you expand, it may show the transfer function. So, okay, any other questions before I go back to the blackboard?
That's the value of PID make an effect on the power conversion.
So actually controller, that's a good question. So PID, basically, if your P is large, D is large, and I is large, essentially the controller effort is going to be large. Now, at the end of the day, what are you trying to do? So you have this mass that is going forward. And then what you are doing is either you are using, okay. Now I have to give you a very simplistic, maybe from physics-based explanation. Imagine that you have this mass. That mass is moving, and you want this mass to stop. Okay, you want this mass to stop at this point. So you are gonna add the controller effort, which is proportional to state. What does that mean? If you are going to add the controller effort, which is proportional to state, what it means, if your mass is farther from the set point, then you are going to apply more and more controller effort. As this mass starts going closer to the set point, your controller effort is going to drop down. Everyone understood this? That is the proportional control. For an example, let me give you another example. Say you walk on Tempe or you walk on Mill Avenue, all of a sudden you see your friend, and you see that friend is far away then what you will do is you will start walking faster so that you can catch up to him or her. Do you agree with me? That is the proportional control. Now, what is the problem with the proportional control? Proportional control is proportional to the distance or the state, but it is not accounting for the inertia. What that means is even though you have controller, because of the inertia effect, there is a possibility that this may overshoot. What it means is you see your friend on the Mill Avenue, you start running and you run fast, but then you pass the friend. You don't stop where your friend is. You actually go past where your friend is stopped. So that is the problem with proportional control. So what do? You do proportional plus derivative, which means as you start going closer and closer, as you know that you start, for example, your friend is walking, and as you start approaching your friend, and as you see the velocity is decreasing, the difference is decreasing, you actually start decreasing the proportional effort. And that is where the derivative term comes in the picture, which means now the controller effort is dependent on the derivative of state, not only how far your friend is, but how fast you are approaching him. Everyone understood this? That is the derivative part. Now, what is the issue with proportional and derivative? Imagine if your friend is walking, you try to catch him up, and then you actually start walking or running fast, and depending upon the relative velocity, which is the error dot, you start manipulating your speed. There is a possibility that there will be some type of offshoot or overshoot or some type of oscillations near where your friend is. You will never be able to go to where your friend is exactly. So what you do there is you add an integral term. What would that integral term do? Integral term would take those oscillations, sum them, because remember, integration is the summation or addition. Sum those oscillations and add controller effort, which is proportional to that oscillations. Everyone understood that? Which means those final oscillations could be eliminated. Everyone understood this from physics point of view? No? Once again. So this is your friend. This is you. You see your friend walking. You want to catch up to him. The logic is, if that friend is farther from you, you walk fast. You started walking fast, but this friend is also walking and you also have inertia. So you cannot stop instantaneously, which means what will happen is you will overshoot. You'll try to slow down, but you will overshoot. Everyone understood this? You have proportional control. The problem is overshoot. How do you eliminate the overshoot? You start walking and now you have this proportional control and you have the derivative term, which is the dependent on the relative velocities or basically error dot. So what is the velocity in between? And then as velocity starts decreasing, you kind of start controlling that controller term. So you kind of go close. You don't overshoot, you kind of go close. But the problem here is because of you have the velocity dependent controller, you are going to have some type of oscillations. Are you with me so far? Now what you do is you add proportional, you add derivative, and you add integral term only when you are close. If you add integral term when you're far away, that will lead to integral wind up. Okay, so integral term is never used on when you are far away from the set point. So you go very close to the set point or where your friend is, and you add the integral term. So what it does, that integral term would add the controller effort that is cumulatively dependent on the oscillations near the set point, which means you will actually go close to the set point. Everyone understood this? That is the physics of PID control. The important point which is not emphasized is integral windup. You'll hear this term again and again and again. What is integral windup? And you can actually, the example which I have shown over here, you can actually play with PID values and see what happens. Integral windup means if you have typically proportional term is big, derivative term is small, and integral term is very small. So proportional term is big, derivative term is small, integral term is very small. So if your integral term is active when the error is very high, when your integral term is active, when the error is very high, remember integral term is integrating the error. Right now you have a large error, but as soon as you start integrating the large error, which means the contribution from the integral controller is going to be very, very high. And that would actually destabilize the system. That is integral windup. So integral term is used when you are very close to set point. PID control, I control is never used if you are far, far away from the set point. If you know for the fact that you are very close to the set point, that is when the I term in PID is turned on. You can play with this, and in next class, I will actually try to show this on using an experimental setup, like what is the effect of PID, and depending upon different PID terms, how you can actually track and control the behavior of the system. I will stop here, and we'll continue the control part in the next class.